Hello, this is a video for lesson 5.5, bases other than E when we are taking derivatives. This should be a quick video, so thank you for watching it. I appreciate that. So notice that in the four statements at the top of the page, there are really two statements. A and B, statements A and B are the same thing except that statement B is more general because it has a U as the exponent, and the same holds for C and D. They are essentially the same statement, or going to be the same rule, except that D is more general. So notice also that A is defined to be a positive number other than 1. U is defined to be we usually define U, a glob or a function of x, okay? So the first rule is that the derivative of a to the x, so that would be something like 2 to the x or 3 to the x, ends up being the natural log of a times a to the x. So we might deduce from that if we had something more general, so our exponent was something more complex than just a naked x, we still would have the natural log of a. We would have a to the u, and then what would be next to it? That's right, by chain rule, it would be du dx, or just u prime, okay? The other rule, sort of like two rules for today, is involving logs of bases other than e. We've seen the derivative of natural log of x. This is logs of bases other than base e. For this, we will have 1 over natural log of a and 1 over x. Those two things together could be written as I just did. Therefore, if we had something more complex as the argument of the log function, we would have 1 over natural log of a times 1 over u times the derivative of u. Okay, so those are our new rules for today, derivatives of bases other than base e. I'm going to take just a few minutes to explain why these rules are what they are. So, first of all, let's think about, I advanced that a little too quick. Let's think about rule A, okay, this first one. And so I hope that you can buy that although I'm doing this in general for an exponent of x, the only difference is with the next one is that chain rule would apply. So I'm not going to be proving chain rule is a thing. I'm just going to prove the more general case, and then hopefully you understand that chain rule would apply anytime it needed to apply. So the first thing I'm going to do is rewrite a to the x as something related to e. So e to the natural log of a is actually a really weird way to write a, and then here's the exponent x. Okay, so these two things are equivalent because the part in the parentheses is equal to a. Now the reason we would rewrite this is because if we didn't know how to find the derivative of a to the x, we do know how to find the derivative of e to the something. So if we were to take the derivative of both sides of this expression now, we would be in business. Okay, also notice, now my pen is a little bit hard on this, my stylus is not perfect. Well, when you have a power to a power, you multiply. So that's what I did in this second line of writing here. Now, we don't know, let's say, how to do this. Say we are, we're deriving the rule that I just mentioned to you, but we do know how to deal with e to the u. This is going to be what I think of as u in my e to the u rule. And the derivative of e to the u is e to the u du. So we will just write e to the u. And then the derivative of this, think about what kind of thing you're looking at. Natural log of a is a number times x. So the derivative of that would just be natural log of a. And then by a log property, we should understand that this part right here can be rewritten as a, right? E to a power and natural log are inverse functions, so they would cancel each other out. We just have a. X is still in the exponent position, and here's natural log of a. So this is actually the rule that we saw at the start of the lesson. This one right here. Okay, so that was the first rule up above. Okay, so that's the derivation. You know I'm not making this stuff up. Okay. The second the second rule that I would like to derive is finding the derivative of the base a log x. Well, again, we're going to try to do that wonderful mathematical technique. If I don't know something, I should write it as something that I do know or understand. And I'm going to use the change of base formula that you guys learned last year and also probably freshman year, 8th grade, depending on your pathway. I'm going to use change of base. So let's say I don't want base A. Instead, let's write this as natural log, or base E. So this guy in the parentheses here is equivalent to what I just wrote over here in red. Okay? Now, you have to think about what kinds of things they are here in red. Natural log of x is a function, but natural log of a is a specific number, because a is a specific number. So I could rewrite this as two different little parts, kind of pull that fraction apart. This part in the front is a constant. It's just a number. Natural log of 2, natural log of 3, natural log of 4, something like that is what's in my denominator there. And as we've discussed, a multiplier, when we take a derivative, is just going to ride along. It comes out of product rule, but that's how it happens. And then we would just have to take the derivative, I'll write this out, the derivative of the other bit. And we know that the derivative of natural log of x is 1 over x. That was our first thing that we learned in this chapter. So there we go. Okay, so that is a way that you can remind yourself of how these derivative rules work in case you happen to be in a situation where you forget either of these rules, okay, and then know that these two rules are the exact same rules, just with chain rule included. Okay, there are now 6 examples that follow, and so let's work through these. When you and your seat partner feel that you are confident, you can pause the video and work ahead if you'd like, and then just start the video again to check your answers, kind of fast forward through it, or you can listen to all 6. That's really fine. Okay, so the first guy here is in the form of a to the x, so we're just going to straight up apply that formula, and we know our derivative is going to be natural log of the base, natural log of 5, times a to the x, or 5 to the x. And that's that, because the exponent was just a plain old naked x, not a u kind of thing. The second one is also in the form of a to the x, but it's more like a to the u, right, because the exponent up here is more complicated than just an x. Nevertheless, we would still have natural log of the base times a to the u, so that would be the same exact thing, and then times the derivative of u, which in this case would be negative 3. Okay, so far so good. 3 is going to require just a smidge more work because this is actually a product. So I'm going to think of this as first times second and then apply the product rule to it. So I know that for question number 3, I'm just going to co-op the space down here. For question number 3, the derivative is going to be first, which is x cubed, times the derivative of the second, which would be natural log of the base, times 3 to the x, plus second, 3 to the x, times derivative of the first, 3x squared. Okay? So it's just pretty straightforward application of formulas, okay? For application of derivative formulas. Question number 4, again, is going to be a product, first times second. So we need to be cognizant of that. So for question 4, f prime of theta, and notice I'm also always labeling. Some of you are very good about this, and some of you need to pay attention to if you mean f of theta versus f prime of theta, and communicate that. So this would be first, and then derivative of sine of 5 theta is actually going to require a teeny chain rule, okay? So the derivative of sine is cosine, and like that, cosine of 5 theta times the derivative of the inside, which would be the 5. So that's first derivative of second that I have so far, plus second, and then the derivative of the first would be natural log of the base times 7 to the theta, or it's like 7 to the x. Okay? Question number 5 is the first one that uses logs of a different base. So this is a base 8 log. So I'm going to have 1 over natural log of 8 and 1 over x. And you could smush that all together as one fraction if you prefer, or leave it separate if that's easier on your brain. It does not matter. Okay? Question number 6 is an instructive sort of question, because certainly I could leave it just how it is and just go at it with my log derivative formulas, but it would be so much easier on my poor brain if I would use log properties first. So notice I'm writing y equals. This is not yet the derivative. I am going to pull this apart using log properties. Okay, so that's a little bit of log property. The 5 can come down in front. That's a little bit more. And now I think using derivatives would be a lot more simple. Okay, so this 5 is just a multiplier that's going to ride along. This part is a base A logarithm, and so I'm going to use that rule from today. Natural log of 3 in the denominator, 1 over x, minus, and then again, this is going to be my other base derivative formula, 1 over natural log of 3 and 1 over x plus 4. The derivative of x plus 4 is 1, so we're good to go. And then I could tidy this up by finding a common denominator and whatnot, but I really don't have to because, you know, calculus. Yay! All right, you should have this worksheet next in your packet. I would like you and your seat partner to do problems 10 through 15 and problem 18 and problem 19 to the best of your ability. And I believe I put an answer key in the packet. Yes, I did. So as you finish problems, you can check one at a time, or you can do the whole block and then check after that. Ask questions as you run into them, and thanks so much.